All right, guys. Hey, we're now at 6.6, the fundamental theorem of calculus and definite integrals. All right, so this is a big dog. I know I say it all the time, but it's a big dog. All right, so now we've seen two major branches of calculus: differential, the tangent line problem, finding slopes, and now the integral, which is the area problem. Leibniz and Newton independently discovered the connection between these two branches, stated informally that differentiation and integration are inverse operations. They wipe each other out. They're opposite. In an earlier lesson, we used the fundamental theorem of calculus part 1 to define new functions, represent accumulation functions, and provide information about the antiderivative. Okay, cool. All right, that's great. Now, the fundamental theorem of calculus part 1, which we kind of already dealt with a little bit, says if f is continuous and you've got this function g, which is from a constant to x, okay, and it's continuous and differentiable, then g prime is going to equal f of x. All right. Alternate notation can be seen by taking the derivative of both sides. And so if you take the derivative of both sides, then it just wipes out the integral. All right. That's what it's saying. So this is kind of a big deal right here. The derivative of the integral wipes each other out. But notice, it's very important. Coming from a constant up to an unknown, a variable. Okay. That's a big deal. Okay, so let's continue with that thought then on the next page. All right, so fundamental theorem says we can define a function, a definite integral of another function, and use the new function. Then the new function is the antiderivative. All right, now part 2 is the one that I always think of as the fundamental theorem of calculus. Okay, so given that f is a rate, all right, then which function big F is changing. All right. So in other words, f of x is the derivative of big F. We've talked about that a lot. We know that from A to B of this is the total net change of F. We've dealt with that stuff. Okay. You've been doing that, adding up all the geometry and all that stuff. Here we go. If function f is continuous on a closed interval from A to B, and big F is the antiderivative of f on A to B, then this is called the definite integral. The definite integral from A to B of f of x dx is big F of b minus big F of a. You can also write it with the prime notation if they give that to you. So if you're given the prime, then the antiderivative of that is going to be the original function names. But remember, when we've been doing this, we had f of x heading to f prime, we talked about this. And then f prime is heading to f double prime. All right, so what heads to f of x then? What do you take the derivative of to get f of x? And we didn't have a name for that, so we use big capital F of x. Now, there's going to be exceptions, there's going to be rules, and there's all kinds of cool stuff that's going to happen because of the chain rule. And so we got to keep that in mind as we're going through this. All right, now, so the definite integral is equal to the net change or displacement, all right, in the antiderivative of f over the same interval. It's commonly known as evaluation theorem. Yeah, never heard that before, but I have heard of the fundamental theorem of calculus, and this is what I think of when we think of the fundamental theorem of calculus right there.